night, we are going to explore one of the quietest yet most profound truths in existence. We are going to travel through the slow, steady expansion of space itself. But before we drift into the deep cosmos, I invite you to subscribe to this channel and perhaps leave a comment below. Tell us where you are listening from tonight and what time it is in your part of the world. It is a small way to connect our own locations before we lose ourselves in the vastness of everything else. Now, let your thoughts settle. Let the room around you fade. We are going to contemplate a motion so large, so slow, and so silent that it is impossible to feel, yet it defines the history and future of everything we know. We are going to talk about how the universe grows. When we think of the beginning of the universe, we often think of a bang, an explosion. We imagine a grenade detonating in an empty room, sending shrapnel flying out into the void. But this image is wrong. It suggests that the universe is expanding into something. It suggests there is an empty box, and the galaxies are rushing to fill it. But there is no box, there is no outside. The universe is not expanding into space. Space itself is expanding. The room is getting bigger. The floor is stretching. The walls are moving away. Imagine a loaf of raisin bread rising in the oven. The dough is the fabric of space. The raisins are the galaxies. As the dough rises, it expands in all directions at once. The raisins are not moving through the dough. They are just sitting there. But the distance between them is increasing. If you were sitting on one raisin, looking at your neighbors, you would see them moving away from you. The further away the raisin, the faster it would seem to move, simply because there is more dough between you and it to expand. This is the nature of cosmic expansion. It is not a race, it is a stretching. To understand this, we must look at the nature of space-time. For thousands of years, humans believed that space was just emptiness, a nothingness that separated objects. It was a stage where the drama of the universe played out, but the stage itself was static. It was neutral. But Albert Einstein taught us that space is not nothing. It is a fabric. It has properties. It can curve. It can twist, and, most importantly, it can stretch. It is elastic. This elasticity means that the metric of the universe, the very definition of a meter or a mile on a cosmic scale, is changing. The ruler we use to measure the cosmos is getting longer every second. This expansion began 13.8 billion years ago. In the very first fraction of a second, the universe underwent a period called inflation. Space expanded exponentially, faster than the speed of light. It smoothed out the wrinkles of the beginning. It set the stage. But even after that initial violent burst, the expansion continued. It slowed down, settling into a calm, steady drift. This is the Hubble flow. It is the river of space that carries the galaxies. It is important to understand that this expansion is incredibly gentle on a local scale. You are not expanding. The Earth is not expanding. The solar system is not expanding. Even our galaxy, the Milky Way, is not expanding. Why? Because gravity is strong. On small scales and in astronomy, small means anything less than a cluster of galaxies. Gravity is strong enough to overcome the expansion. It holds things together. The atoms in your body are held together by electromagnetic forces that are far, far stronger than the gentle stretching of space. Imagine two people holding hands in a crowd that is slowly drifting apart. As long as they hold on tight, they stay together. The crowd moves around them, but their connection remains. Gravity is that hand-holding. So expansion is something that only happens in the immense voids between the galaxies. It is a phenomenon of the deep emptiness. It is where gravity is weak that space is free to grow. This growth is silent. There is no friction in a vacuum. There is no wind rushing past the stars. The galaxies drift apart in absolute silence. It is the most peaceful motion imaginable. For most of human history, we had no idea this was happening. We looked up at the night sky and saw a static tapestry. The stars seemed fixed. The constellations looked the same to the Egyptians as they do to us. The universe felt eternal and unchanging. It wasn't until the 1920s that we realized the truth. An astronomer named Edwin Hubble was looking at nebulae, fuzzy patches of light in the sky. At the time, we thought these were gas clouds inside our own galaxy. But Hubble realized they were islands. They were other galaxies, millions of light years away. And when he measured their light, he found something shocking. They were all moving away from us. He noticed a pattern. A galaxy that was 1 million light years away was moving at a certain speed. A galaxy that was 2 million light years away was moving twice as fast. A galaxy 3 million light years away was moving 3 times as fast. This relationship, distance equals speed, is known as Hubble's law. It was the first proof that the universe was not a static box, but a living, growing entity. It meant that if you ran the movie backward, everything would come together. It pointed to a beginning. But let us stay in the present moment of expansion. Imagine floating in the intergalactic void. You are millions of light years from the nearest star. It is dark. The only light comes from distant fuzzy blobs, entire galaxies reduced to smudges. In this void, new space is being created every second. It is bubbling up from nowhere. It is a fountain of emptiness. This concept creates a paradox in our minds. Where does the new space come from? Is it being stretched thin, like a rubber band? Or is new fabric being woven? The answer lies in the nature of dark energy, which we will explore later. But effectively, space is not conserving its volume. It is generating more volume. It is the ultimate renewable resource. Because space is expanding, the universe has no center. If you go back to the raisin bread analogy, every raisin sees every other raisin moving away. Every raisin thinks it is the center of the expansion. We, here on Earth, see all the galaxies rushing away from us. It looks like we are the center of a cosmic explosion. But an observer in the Andromeda galaxy would see the exact same thing. They would see the Milky Way rushing away from them. Everyone is the center, and no one is. This is the cosmological principle. It states that the universe looks roughly the same from every location. It is a democracy of perspective. There is no privileged place. The expansion also creates a horizon, because the speed of expansion increases with distance. Eventually, there is a point where the galaxies are receding faster than the speed of light. Wait, faster than light. Doesn't Einstein say nothing can travel faster than light? Einstein said that nothing can travel through space faster than light. But space itself can do whatever it wants. It is not bound by the speed limit of the particles within it. Space can expand at superluminal speeds. This creates a cosmic event horizon. Beyond a certain distance, the space between us and a galaxy is stretching so fast that the light from that galaxy can never reach us. It is trying to swim upstream against a current that is moving faster than it can swim. this light is swept back into the darkness. It is lost to us forever. The universe has an edge, not a physical wall, but a visual limit. We are trapped in a bubble of observable light, surrounded by an infinite ocean we can never see. But inside our bubble, the view is magnificent. We can see billions of years into the past. Because light takes time to travel, looking out into space is looking back in time. When we look at a distant galaxy, we are seeing it as it was when the universe was smaller. We are seeing it in a time when the galaxies were closer together. We can trace the expansion back. We can see the universe getting denser and hotter the further back we look. We can see the evolution of the growth. This expansion is not just a matter of distance, it is a matter of temperature. As the universe expands, it cools. Think of a bicycle pump. When you compress air, it gets hot. When you release air, expanding it, it gets cold. The universe is a gas that has been expanding for 13 billion years. It started at billions of degrees. Today, the average temperature of space is minus 270 degrees Celsius, just 3 degrees above absolute zero. The universe has chilled out. It has relaxed. This cooling allowed matter to form. It allowed atoms to stick together. It allowed gas to collapse into stars. The expansion is the reason we are here. If the universe had stayed hot and dense, life would never have been possible. We need the cold dark to survive. The expansion also affects light itself. As a photon of light travels through expanding space, the wave is stretched. Imagine drawing a wave on a rubber band. If you pull the rubber band, the wave gets longer. The peaks move further apart. In physics, a longer wavelength means a redder color. Blue light is short and tight. Red light is long and loose. So, as light travels through the expanding universe, it turns red. This is redshift. It is not the star changing color. It is the space between the star and your eye that is stretching the light. It is a signature of the journey. The farther away a galaxy is, the more its light has been stretched. The redder it looks. By measuring this redness, we can tell how far the light has traveled and how much the universe has grown since the light left its source. This redshift is a quiet, constant reminder of the motion. Every photon from the deep universe arrives at Earth a little tired, a little stretched, having navigated the growing tide of space-time. But what drives this expansion? For a long time, we thought it was just the leftover momentum from the Big Bang, like a coasting car. We assumed that gravity would eventually slow it down. We thought the universe was like a ball thrown into the air. It goes up, but gravity pulls it back. We expected the expansion to decelerate. But in the late 1990s, we found something startling. We looked at distant supernovae, exploding stars, and found they were dimmer than they should be. They were farther away than the math predicted. The universe is not slowing down, it is speeding up. The ball thrown into the air isn't falling back. It's accelerating upward into the sky. Something is pushing it, something unknown. We call this dark energy. It is a placeholder name for a mystery. It seems to be a property of space itself. As space expands, it creates more dark energy, which pushes space apart faster, which creates more dark energy. It is a runaway train. Gravity is losing the war. This means the universe is destined to become darker, colder, and emptier. The galaxies will be pushed so far apart that they will become invisible to each other. But that is a story for trillions of years in the future. For now, we are living in the golden age of astronomy. We live in a time when the galaxies are still close enough to see, but far enough apart to exist safely. We live in the perfect balance. As we drift through this concept of expansion, try to visualize it not as a violent tearing, but as a blooming, a flower opening. The petals of the cosmos are unfurling. It is a gentle, silent process. It is creating room. Room for what? Room for time. Room for possibilities. Without expansion, the universe would have crunched back into a singularity long ago. Expansion buys us time. It buys us existence. Every second you breathe, the universe gets a little bigger. The distance between the Milky Way and the distant quasars increases by millions of kilometers. You don't feel it. The ground beneath you is solid. The gravity of Earth holds you tight. But out there, in the deep silence, the great drift continues. It is a comforting thought. The universe is not a cage. It is an open field getting wider every moment. It is boundless. There is no wall at the end of the universe. There is only more space, being born from the void, endlessly, quietly, perfectly. This expansion connects the very small to the very large. It connects the quantum vacuum to the clusters of galaxies. In the next chapter, we will look at the fabric itself. We will look at space-time. We will explore what it means for space to be curved and stretched. We will look at the grid lines of the universe. We will see how mass tells space how to curve, and how space tells mass how to move. We will move from the idea of growth to the idea of structure. We will see how the universe is not just getting bigger, but getting more complex. For now, imagine the night sky. Imagine the stars you see are not fixed points on a ceiling, but lights on ships sailing away from you on a dark, calm ocean. They are drifting. You are drifting. We are all floating in the great expansion. Rest in the movement. Rest in the vastness. The universe is making room for you. We have witnessed the initial breath of the universe. We have seen space unfurl from a singularity, stretching faster than light, smoothing out the chaotic energy of the beginning. But the story of expansion is not a single, steady line. It is a drama with distinct acts, and the act that followed the Big Bang was not one of acceleration, but of deceleration. Imagine a stone thrown high into the air. It rises, but as it rises, the gravity of the Earth pulls at it. The ascent slows. The stone climbs, but with less and less energy, fighting the invisible hand that wants to bring it back down. For the first 9 billion years of its life, the universe was that stone. The initial kick of the Big Bang was immensely powerful. It sent matter and energy flying outward in all directions, but the universe was crowded. It was filled with a dense fog of particles, dark matter, hydrogen gas, photons, and all of this matter possessed gravity. Every atom in the cosmos was pulling on every other atom. The gravity of the universe was trying to crush the universe back into a ball. It was a cosmic tug-of-war. On one side, the momentum of the expansion, pushing outward. On the other side, the attractive force of gravity, pulling inward. For eons, it looked like gravity might win. The expansion slowed down. The galaxies, as they formed, drifted apart, but they drifted apart slower and slower every billion years. The universe was coasting uphill against the gradient of its own mass. This period is known to cosmologists as the matter-dominated era. It was a time of profound change, driven entirely by the changing geometry of space. As the universe expanded, the density of matter dropped. Think of a drop of ink falling into a swimming pool. At first, the ink is dark and concentrated, but as it spreads through the water, it becomes paler, thinner, more diffuse. The matter of the universe was diluting, and as it diluted, the temperature fell. This cooling is the unsung hero of cosmic history. We often focus on the formation of structures, stars and galaxies, but none of that could have happened without the expansion creating the necessary cold. Heat is the enemy of structure. In a hot universe, particles move too fast to stick together. They bounce off one another like billiard balls. Gravity cannot take hold because the thermal energy is too strong. It pushes back. To build a universe, you need to calm the particles down. You need to freeze them into place. The expansion of space acts as a global refrigerator. As space stretches, it steals energy from the particles moving through it. The wavelengths of photons get longer. The velocities of gas atoms get slower. The universe chills. This cooling allowed the first great transition, the formation of atoms. We touched on this in the story of light, but let us look at it from the perspective of space. Before this moment, the universe was a plasma, a soup of charged particles. Light was trapped, bouncing endlessly between electrons. Space was opaque. But as the temperature dropped below 3,000 degrees Kelvin, the electrons slowed down enough to be captured by protons. They formed hydrogen. The fog cleared. The universe became transparent. This moment, recombination, released the cosmic microwave background radiation, but it also did something else. It released matter from the grip of radiation. Before this, the intense light of the Big Bang blew the gas apart, preventing it from clumping. But once the light escaped, the gas was left behind in the dark. It was cold, it was neutral, and it was vulnerable to gravity. This is when the cosmic web began to form. The expansion was still happening, stretching the voids between things, but in the slightly denser regions, gravity began to win the local battles. Dark matter, which makes up the bulk of the mass in the universe, had already begun to collapse. It formed vast, invisible sheets and filaments stretching across the cosmos. These filaments acted as the skeleton of the universe. The ordinary gas, the hydrogen and helium, flowed into this skeleton. It streamed down the gravitational valleys, gathering in the knots where the filaments intersected. Imagine a spider web covered in dew. The silk strands are the dark matter. The water droplets gathering on the silk are the gas clouds that will become galaxies. The empty spaces between the strands are the voids. As the universe expanded, these voids grew larger. They are the emptiest places in existence. Regions of space hundreds of millions of light years across containing almost nothing. No galaxies, no stars, just a few lonely hydrogen atoms drifting in the absolute dark. The expansion of the universe is largely the story of these voids getting bigger. They swell, pushing the filaments of matter apart. The matter concentrates into thinner and thinner sheets, while the empty spaces dominate the volume. The universe becomes a foam. This structure is not random. It is the result of sound waves from the Big Bang frozen into the sky. In the very early universe, when it was a dense plasma, sound waves rippled through the fluid. These were pressure waves. compressing the gas in some places and rarefying it in others. When the universe cooled and became transparent, these waves were frozen in place. Rate 100%, pitch 1%. The peaks of the waves became the locations of the future galaxy clusters. The troughs became the voids. We can still see this pattern today in the distribution of galaxies. It is called baryon acoustic oscillations. It is the fossilized sound of creation, stretched by the expansion of space until the wavelength of the sound is 500 million light-years long. So, as we drift through this era of the universe, the first few billion years, we see a universe that is separating. The dense parts are getting denser, collapsing under gravity to form stars and galaxies. The empty parts are getting emptier, stretched by the expansion. It is a process of distillation. The universe is sorting itself out. But even as the galaxies formed, they were moving away from each other. The space between the knots of the web was stretching. This brings us to the concept of proper distance versus comoving distance. Imagine drawing two dots on a balloon. The proper distance is the distance you would measure with a ruler right now. The comoving distance is a coordinate system that expands with the balloon. In the expanding universe, the galaxies stay at the same comoving coordinates. They are not moving through space in a way that changes their address. But the proper distance, the amount of physical space between them, is increasing constantly. This distinction is crucial because it explains why we don't feel the expansion. The gravity of our galaxy holds our stars at a fixed, proper distance from the center. The solar system is bound by the sun's gravity. Your body is bound by electromagnetic forces. We are islands of stable, proper distance floating in a sea of expanding, comoving distance. We are the rocks in the river. The water flows around us, but we do not expand with it. This era of deceleration, where gravity was breaking the expansion, had a profound effect on the destiny of the cosmos. It allowed the universe to last. If the initial expansion had been too fast, gravity would never have been able to catch the gas. The matter would have been flung apart too quickly to form stars. The universe would have been a cold, dark, thin mist of particles forever. No light, no life. If the initial expansion had been too slow, gravity would have won too easily. The universe would have collapsed back into a singularity almost immediately. A big crunch would have happened before the first star could ignite. But we live in a Goldilocks universe. The rate of expansion and the density of matter were perfectly balanced. It was expanding just fast enough to avoid recollapse, but slow enough to allow structure to form. This balance is one of the greatest mysteries in physics. It is known as the flatness problem. The universe appears to be geometrically flat. This means that parallel lines stay parallel forever. They never meet and never diverge. For this to be true, the density of the universe had to be tuned to a precision of 1 part in a trillion trillion at the moment of the Big Bang. We believe this tuning was accomplished by inflation, the rapid expansion in the first fraction of a second. Inflation stretched space so flat that any initial curvature was smoothed out, just as inflating a beach ball makes the surface look flat to an ant walking on it. So, for billions of years, the universe coasted. It grew, but the growth was slowing down. The spacing between the galaxies increased, but the pace of that increase was dropping. To an observer living in this time, say 5 billion years after the Big Bang, the future would have seemed clear. Gravity was the dominant force. Eventually, they might have thought the expansion would stop. The galaxies would hang suspended for a moment, and then the Great Fall would begin. The universe would breathe in. But they would have been wrong, because lurking in the shadows, hiding in the empty space itself, was a force that had not yet shown its hand. Dark energy. In the early universe, the universe was small and dense. The gravity of the matter was incredibly strong. Dark energy, which is a property of space itself, was weak by comparison. There wasn't enough space for it to matter. Gravity drowned it out. But as the universe expanded, the matter got diluted. The density of stars and gas dropped. Gravity got weaker. However, dark energy does not dilute. It is constant. If you double the amount of space, you double the amount of dark energy. It doesn't get thinner. You just get more of it. So, as the eons passed, the balance of the power began to shift. Gravity was fading. Dark energy was growing. It was a silent coup. Around 5 billion years ago, coincidentally, just as our own sun was being born, the scales tipped. The density of matter dropped below the density of dark energy. The deceleration era ended. The stone that had been thrown into the air stopped slowing down. It hung there for a cosmic moment, and then, impossibly, it began to speed up. The universe entered the acceleration era. The expansion began to run away. The brake pedal was released, and the accelerator was pressed. But let us remain in the time before this acceleration, the time of structure formation, the time when the galaxies were closer together. Imagine the sky of a planet living in this younger universe. The night sky would have been far more brilliant than ours. Because the universe was smaller, the galaxies were packed tighter. You might see the Andromeda Galaxy not as a faint smudge, but as a giant spiral spanning 10 degrees of the sky. You might see galaxy collisions happening all around you, great splashes of stars merging in the dark. It was a time of intimacy. The universe was a busy, crowded place. The light from one galaxy could easily reach another. The cosmic horizon, the limit of what we can see, was expanding, revealing more and more of the universe every day. Light was winning the race against the expansion. Photons emitted by distant galaxies could swim upstream against the stretching of space and eventually land on a telescope. The observable universe was growing faster than the physical universe was stretching. It was the golden age of connectivity. Information could travel. The causal structure of the cosmos was knitting itself together. This expansion also created time, or rather, it created the arrow of time. Entropy, the measure of disorder, increases as the universe expands. In a small, hot universe, there's very little room for disorder. Everything is compressed. But as the universe grows, the number of possible arrangements of atoms increases exponentially. The expansion provides the headroom for entropy to grow. It provides the empty space into which heat can dissipate. Without expansion, the universe would have reached thermal equilibrium, heat death, billions of years ago. The stars would have cooked themselves in their own radiation. By expanding, the universe kept the sky cold. It ensured that the night sky is dark. This is Olber's paradox. If the universe were static and infinite, every line of sight would end on a star. The entire sky would be as bright as the surface of the sun. We would be roasted. But because the universe is expanding, the light from distant stars is stretched and dimmed. The expansion makes the night dark. It creates the heat sink into which the sun can dump its energy. Life relies on this temperature difference. We rely on the expansion to keep us cool. So, the expansion of space is not just a distant, abstract phenomenon. It is the reason the Earth is habitable. It is the cooling system of the biosphere. As we drift through this middle era of the universe, we see the galaxies settling down. The violent collisions of the early days become less frequent. The spirals tighten. The elliptical galaxies relax into glowing spheres. The expansion carries them gently apart. They become islands in the stream. The voids between them grow deeper and darker. The filamentary web of dark matter stretches thin, but it holds. In our own corner of the universe, the local group forms. This is our neighborhood. It contains the Milky Way, Andromeda, and about 50 smaller dwarf galaxies. Interestingly, the local group is one of the few places where gravity has permanently won. The gravity between the Milky Way and Andromeda is strong enough to overcome the expansion of the universe. We are bound together. While the rest of the universe rushes away from us, Andromeda rushes toward us. We are a gravitationally bound system. Even as the universe expands to infinity, our little cluster of galaxies will stay together, a lifeboat in the expanding dark. But look beyond our local island. Look at the Virgo cluster, 50 million light-years away. The gravity is trying to pull us toward it, but the expansion is pushing us away. It is a tug-of-war that is currently a stalemate, but the expansion is slowly gaining strength. Look further to the Coma cluster. It is drifting away. The light leaving it today will take 300 million years to reach us, and when it arrives, it will be redder than it is now. The universe is stretching the light. It is writing its signature on every photon. In the next chapter, we will explore this redshift in detail. We will look at how light acts as the cosmic speedometer. We will see how Edwin Hubble decoded the rainbow to discover the expansion. We will look at the Doppler effect and how it applies to the fabric of space. We will understand why distant galaxies look red and what that tells us about the age of the universe. We will also look at the concept of time dilation on a cosmic scale, how we see distant events happening in slow motion because the light pulses are stretched out as they travel to us. The universe is a slow-motion movie. For now, simply feel the space around you. It seems empty and still, but it is part of the great river. The space between your eyes and this screen is expanding. It is expanding too slowly to measure, less than the width of an atom over the age of the universe. But it is happening. You are embedded in a fabric that is growing. You are part of a universe that is making room for the future. Rest in that openness. The universe is not closing in on you. It is opening up. We have seen the first stars ignite, tearing through the fog of the dark ages. We have seen them live fast and die young, seeding the universe with heavy elements. But the universe is not just a collection of lonely stars drifting in isolation. It is a collection of cities. It is a landscape of structure. Now, we must watch these cities rise. We must watch gravity pull the scattered lights together into the magnificent swirling structures we call galaxies. This is the era where the universe begins to look like the home we recognize today. It is the era of construction. This process begins in chaos. The early universe, a billion years after the Big Bang, is a violent, crowded place. The first proto-galaxies are not the elegant, majestic spirals we see in our telescopes now. They are messy, irregular blobs of gas and stars. They are train wrecks in slow motion. Gravity is relentless. The dark matter halos, the invisible skeletons we spoke of in the last chapter, are merging. They are falling into one another. As they crash, they drag the visible matter, the glowing gas and the newborn stars, along with them. These collisions are the building blocks of structure. It is a process of hierarchical assembly, small things merging to become big things. Imagine two massive clouds of gas falling toward each other across the void. As they approach, they don't just smash head-on. They swing past each other, caught in a gravitational dance. They spiral inward, missing the direct collision but trapped by their mutual pull. And as they spiral, they begin to spin. This is the birth of angular momentum on a galactic scale, the conservation of spin. It is one of the fundamental laws of physics. Just as a figure skater spins faster when she pulls her arms in, the collapsing gas cloud spins faster as it shrinks. The enormous, lazy rotation of the dark matter halo is transferred to the gas, amplifying the speed. This spin has a profound effect on the shape of the galaxy. Gravity wants to pull everything into a sphere, a ball. That is the shape of least resistance, but the spin fights back. The centrifugal force pushes the material outward at the equator. It resists the collapse in one direction, but allows it in the other. The result is a compromise, a disk. The messy blob flattens out. It becomes a pancake of stars rotating around a central core. This is how the spiral galaxy is born. It is a physical balance between the pull of the center and the speed of the spin. It is gravity versus momentum, frozen in the shape of a wheel. But the center is not empty. In the heart of every forming galaxy, a monster is growing. The supermassive black hole. We still do not know exactly how they got there so quickly. It is a puzzle. Some may have formed from the collapse of the very first population 3 stars. Others may have formed from the direct collapse of massive gas clouds that never became stars at all. However they were born, they are hungry. They sit at the bottom of the gravitational well, where the gas is thickest. They feed. As the gas spirals into the black hole, friction heats it up to millions of degrees. It shines with the light of 1,000 galaxies. This is a quasar. Quasars are the lighthouses of the infant universe. They are visible across billions of light years, beaming X-rays and ultraviolet light into the cosmos. But they are not just passive lights. They are engines. They are thermostats. The energy pouring out of a quasar is so intense that it pushes back against the infalling gas. It creates a galactic wind. This wind blows the gas out of the center of the galaxy, pushing it back into intergalactic space. It starves the black hole and stops the formation of new stars. This is a crucial feedback loop. The black hole regulates the growth of the galaxy. If the galaxy tries to grow too fast, the black hole wakes up and blows the fuel away. If the galaxy stops growing, the black hole starves and goes to sleep. They are locked in a symbiotic relationship, growing together over billions of years, sizing each other up. While the black hole manages the center, the disk is busy making stars. In these early days, the star formation rate is incredibly high. It is a starburst era. The galaxies are factories running at maximum capacity. gas clouds collapse, ignite, and explode as supernovae all within a few million years. The explosions send shock waves through the disk, compressing nearby gas and triggering the collapse of neighboring clouds. It is a chain reaction of creation, fire igniting fire. The galaxy glows blue with the light of hot, young stars. But it is also dusty. The supernovae produce vast amounts of soot and dust, complex carbon molecules. This dust blocks the visible light, making the young galaxies look dark and shrouded to our human eyes. But if we look in the infrared, using telescopes like the James Webb, the dust glows. We can see the heat of the nursery. We can see the stars being born inside their cocoons, wrapped in warm blankets of silicate and carbon. Over time, the collisions become less frequent. The universe is expanding, moving the galaxies further apart. The frantic mergers of the early days slow down. The universe begins to mature. The galaxies have time to settle. The chaotic currents in the disk smooth out. The spiral arms emerge. These arms are not solid structures. They are not rigid spokes like on a wagon wheel. They are density waves. Imagine a traffic jam on a highway. The cars slow down as they enter the jam and speed up as they leave. The jam itself moves slowly or stays in one place, even though the cars are passing through it. A spiral arm is a gravitational traffic jam. As gas clouds move into the spiral arm, they get compressed. They slow down. The compression triggers star formation. Then, the stars move out of the arm and continue their orbit. The spiral arm is a standing wave of star formation, a permanent pattern made of temporary stars. It is a region where the galaxy is lit up. It is beautiful. It is the signature of order emerging from chaos, the golden ratio written in starlight. And among these settling galaxies is our own, the Milky Way. It began as a small clump of dark matter and gas. It grew by swallowing its neighbors. It ate smaller dwarf galaxies, stealing their stars and their gas. We can still see the remnants of these meals today. Streams of stars circling the Milky Way halo are the crumbs of galaxies that were digested billions of years ago. Our galaxy is a cannibal, but it is a benevolent cannibal. It uses the stolen material to build. It incorporates the strangers into the main disk. About 9 billion years after the Big Bang, about 4.5 billion years ago, something happened in a quiet spiral arm of the Milky Way, a relatively boring neighborhood called the Orion Spur. A cloud of gas and dust, enriched by the deaths of previous generations of stars, began to collapse. Maybe it was nudged by the shockwave of a nearby supernova. Maybe it just got too heavy and crossed the critical density threshold. It shrank, it spun, it flattened into a disk, and in the center a yellow star ignited. Our sun. It was not a monster star. It was modest, stable. It was a main sequence star, type G, designed to burn slowly for billions of years. It was the perfect hearth for a long story. It was bright enough to warm a planet, but calm enough not to sterilize it every week with flares. Around the new sun, the leftover dust and gas formed a disk, the protoplanetary disk. This was the leftover material, the scraps from the formation of the star. In this disk, the dust grains began to stick together. Electrostatic forces, static electricity, pulled them into tiny clumps, dust bunnies in space. Then, as they grew larger, gravity took over. The clumps became pebbles. The pebbles became boulders. The boulders became planetesimals, mountains. floating in space. It was a violent shooting gallery. The planetesimals smashed into each other. Some shattered into dust, others merged. The winners grew larger. They swept up the material in their orbits, clearing their lanes. Close to the sun, where it was hot, only rock and metal could survive. The volatile gases boiled away. This formed the inner planets: Mercury, Venus, Earth, Mars, small, dense, rocky worlds. Further out, past the frost line, it was cold enough for water, ammonia, and methane to freeze into ice. Here, the planets could grow huge. They had more building material, ice as well as rock. They grew so massive that their gravity could capture the light gases, hydrogen and helium, before the sun blew them away. This formed the gas giants: Jupiter, Saturn, Uranus, Neptune. They are failed stars, balls of gas that never ignited. The Earth, in those early days, was not a blue marble. It was a ball of molten magma. It was hell. We call this the Hadean Eon, named after Hades, the underworld. It was bombarded by asteroids and comets. The surface was a roiling ocean of lava. The atmosphere was toxic. There was no water, no oxygen, no life. And then, the final catastrophe occurred. A Mars-sized object, a wayward protoplanet named Theia, smashed into the young Earth. It was a glancing blow, but it was devastating. The impact melted the Earth's crust completely. It splashed a massive ring of molten rock into orbit around the planet. For a few thousand years, Earth had a ring like Saturn, but made of lava. Gravity gathered this ring together. It coalesced into a single sphere, the Moon. The Moon is the child of the Earth, born from fire. Its gravity stabilized the Earth's wobble, creating the regular seasons we know today. Without the Moon, Earth might have been a chaotic, tumbling world with wild climate swings. For millions of years after the impact, the Earth cooled. A crust formed, black basalt floating on the mantle. Volcanoes erupted, spewing steam and carbon dioxide into the atmosphere. The sky was red and heavy. Comets, carrying ice from the outer solar system, rained down. They were the delivery trucks of the cosmos. They delivered the water. The steam in the atmosphere condensed. It rained. It rained for centuries. It rained for thousands of years without stopping. The basins filled. The first oceans were born. The stage was set. The physics was done. The chemistry was ready. The planet was wet, warm, and rich in minerals. But the universe was still a dangerous place. The young sun was dim, 30% dimmer than today, but it was prone to violent flares. The solar system was filled with debris. Life, if it was to start, would have to be tough. It would have to start in the deep, protected places, away from the UV radiation, away from the asteroid impacts. The story of the universe, from the first second to the formation of the Earth, is a story of cooling. It is a story of energy spreading out, finding new forms. From the quark-gluon plasma to the proton, from the proton to the atom to the star, from the star to the heavy element, from the element to the dust, from the dust to the planet. It is a cascade of complexity. Each step builds on the one before. Each step is unlikely, yet inevitable given enough time. And now, on this wet, rocky world, a new kind of complexity was about to emerge. A complexity not of nuclear fusion or gravity, but of information, of biology. In the next chapter, we will watch the spark of life. We will not look at how it started. That remains a mystery locked in the deep past. But we will look at what it did. We will see how single-celled organisms terraformed the planet. We will see the great oxygenation event, where blue-green algae poison the atmosphere with oxygen, killing almost everything but paving the way for us. We will see the slow climb from the ocean to the land. We will see the Earth turn green. But for now, hover above the young Earth. It is 4 billion years ago. The moon is much closer, huge in the sky. It orbits faster, raising tides of 1,000-foot waves that rush across the global ocean, scrubbing the continents. The air is red with methane and carbon dioxide. There is no green. It is a harsh, alien world, but it is home. It is the result of 9 billion years of cosmic evolution. Everything that happened in the first second, the ratio of matter to antimatter, the strength of gravity, the speed of light, conspired to create this rock, this water, this moment. The constants of nature were tuned for this. You are the result of that conspiracy. The atoms in your hand were once inside a star that died to make you. The water in your blood was once ice on a comet, drifting past Neptune. Rest in that deep connection. You are not in the universe. You are of it. You are the universe taking shape. Drift in the orbit of the young sun. Feel the potential waiting in the water. The long wait is over. The awakening is about to begin. We have watched the galaxies drift apart, carried by the silent river of expanding space. We have seen them settle into islands, separated by growing voids. But how do we know this is happening? We cannot feel the expansion. We cannot see the galaxies moving with the naked eye. They appear frozen in the amber of the night sky. To see the motion of the universe, we must learn to read the only message that can cross the void. We must read the light. Light is not just illumination, it is information. It is a code that carries the secrets of its source, its temperature, its composition, and most importantly, its speed. To decode this message, we must understand the nature of the signal. Light travels as a wave. It is a ripple in the electromagnetic field, oscillating up and down as it flies through the vacuum. The distance between two peaks of this wave is called the wavelength. Our eyes interpret this wavelength as color. Short, tight waves are blue. Medium waves are green. Long, lazy waves are red. This is the spectrum of the rainbow. But the spectrum is fragile. It can be changed. It can be stretched. Imagine you are standing by a train track. In the distance, a train approaches, blowing its whistle. As it rushes toward you, the sound is high-pitched, a scream. The sound waves are being squashed together by the speed of the train, shortening their wavelength. But as the train passes you and speeds away, the sound drops. The scream becomes a moan. The pitch lowers. This is because the sound waves are now being stretched out behind the train. This is the Doppler effect. It applies to sound and it applies to light. If a star moves toward us, its light waves are compressed. They turn blue. This is blue shift. If a star moves away from us, its light waves are stretched. They turn red. This is red shift. In the early 20th century, astronomers began pointing their spectroscopes, instruments that break light into rainbows, at the fuzzy nebulae in the sky. They expected to see a mix, some moving toward us, some moving away, just like gas molecules in a balloon move in random directions. But that is not what they found. When Edwin Hubble and his assistant Milton Humason analyzed the light from these distant islands, they saw red. Almost everywhere they looked, the light was shifted toward the red end of the spectrum. And it wasn't just a subtle shift. The farther away the galaxy was, the redder it appeared. A galaxy nearby might be moving away at 1,000,000 miles an hour. A galaxy twice as far away was moving at 2,000,000. A galaxy 3 times as far, 3,000,000. This was the smoking gun. This was the proof that the universe was not static. It was exploding outward. But here, we must make a crucial distinction. A distinction that is often misunderstood, but which is the key to understanding the cosmos. The galaxies are not moving through space away from us, like shrapnel from a bomb. If they were, we would be at the center of the explosion, which is statistically impossible. Instead, space itself is expanding between us. This is cosmological redshift. It is different from the Doppler effect. The Doppler shift happens when the source moves. Cosmological shift happens when the road moves. Imagine drawing a wavy line on a rubber band. The line represents a light wave. Now, stretch the rubber band. The wave gets longer. It stretches out. The peaks move further apart. The light hasn't changed its nature. The fabric it is traveling on has grown. This is what happens to a photon as it crosses the intergalactic void. It leaves a distant star as blue light. It flies for 1,000,000,000 years. During that 1,000,000,000 years, the universe expands. The space the photon is traveling through stretches, and because the photon is embedded in space, it stretches too. By the time it hits your telescope, it is red. It is tired. It has lost energy. The expansion of the universe has literally sapped the strength of the light. This tells us that the universe is a cooling engine. It is taking the high-energy fire of the Big Bang and stretching it into the low-energy chill of the deep future. But how do we know it is redshift? How do we know the star isn't just naturally red? There are red stars after all. We know because of the barcodes. When light leaves a star, it passes through the star's atmosphere. The atoms in that atmosphere, hydrogen, helium, calcium, absorb very specific wavelengths of light. They leave dark lines in the rainbow. These are called Fraunhofer lines. These lines act as a fingerprint. Hydrogen always absorbs light at exactly the same frequencies. It creates a specific pattern of gaps, like a barcode. When Hubble looked at distant galaxies, he saw this hydrogen barcode, but it was in the wrong place. The whole pattern had been shifted to the right, toward the red. It was like sliding a stencil over a drawing. The pattern was identical, but the position had changed. This proved that the light was being stretched. The amount of this shift is represented by the letter Z. A zs of 0 means no shift. A zetaton of 1 means the wavelength has doubled. The universe has doubled in size since that light was emitted. We have seen galaxies with a redshift of AZ equals 13. This means the universe has expanded by a factor of 14 since that light left its source. The light from these galaxies left them when the universe was only a toddler. It has been traveling for 13.4 billion years, stretching all the while. When it started, it was blinding ultraviolet light. Now, it arrives as invisible infrared light. We cannot see it with our eyes. We need special telescopes, like the James Webb, which are designed to see heat rather than light, to detect these ancient ghosts. This stretching has a profound consequence for how we perceive the universe. It means that the farther we look, the darker things get. The light is being diluted. Not only is it spreading out over a larger area, the inverse square law, but each individual photon is carrying less energy because of the redshift. If you could look far enough, to the edge of the observable universe, the light is shifted so far that it becomes microwaves. This is the cosmic microwave background we spoke of. It is the wall of fire from the Big Bang, redshifted by a factor of 1100. The fire has become a faint hum, but redshift affects more than just color. It affects time. This is one of the most mind-bending aspects of cosmology. The expansion of space stretches the gap between events. It creates a slow motion effect. Imagine a distant supernova. It explodes. The explosion takes, say, 20 days to fade away. It sends out a stream of photons. The first photon leaves on day 1. The last photon leaves on day 20. These photons travel toward Earth, but as they travel, space expands. The distance between the first photon and the last photon increases. They get spread out. By the time they arrive at Earth, billions of years later, the gap between them has doubled. The first photon arrives. We start our clock. We wait for the last photon. It doesn't arrive in 20 days. It arrives in 40 days. To us, looking through the telescope, the explosion seems to take twice as long as it actually did. We are watching the past in slow motion. This is cosmological time dilation. We have measured this. We watch supernovae at different distances. The further away they are, the slower they seem to explode. A standard bomb that takes 2 weeks to detonate nearby takes 4 weeks to detonate at redshift 1. At the edge of the universe, time seems to crawl. If there were a clock on a distant quasar, we would see it secondhand taking minutes to tick. And they, looking back at us, would see our clocks running slow too. This is the relativity of the expanding cosmos. We are trapped in our own time bubble, and everyone else appears to be moving through molasses. This stretching applies to information, too. If an alien civilization in a distant galaxy tried to send us a message, a radio broadcast, the signal would be stretched. Their high-pitched voices would become deep bass. Their rapid data stream would become a slow, lethargic pulse. Communication across the cosmos is fighting against the tide of expansion. The universe is working to isolate us, to slow down the conversation until it stops. This brings us back to the idea of the horizon. Because the expansion is accelerating due to dark energy, there's a point where the recession velocity exceeds the speed of light. Regions of space are moving away from us faster than light can travel. This does not violate Einstein's rules because it is space expanding, not objects moving. But it creates a boundary, the cosmic event horizon. Any light emitted beyond this horizon will never reach us. It is like a runner on a treadmill that is moving faster than she can run. She will be swept backward. The light is swept away into the dark. This horizon is shrinking. Or rather, more and more galaxies are crossing it, leaving our observable bubble. Every day, galaxies that we could once see drift across the line and vanish. They are disconnected from our causality. They are gone forever. We are losing the universe. Piece by piece, galaxy by galaxy, the cosmos is redshifting out of existence. Eventually, in the far future, the local group of galaxies, Milky Way and Andromeda, will be the only things left in the visible sky. All the other billions of galaxies will have been swept over the horizon. The sky will be dark, save for our own stars. Future astronomers will look up and see a static, lonely universe. They will not see the expansion. They will not see the Big Bang's afterglow, which will have stretched into undetectable radio waves. The evidence of our origins is being erased by the expansion itself. We are living in a privileged time. We live in the era where the light can still reach us. We can still read the history of the universe written in the redshift. We can still see the echo of the beginning. Let us return to the photon's perspective. Imagine being that particle of light. You are born blue and hot. You fly through the void for eons. You feel the space around you growing. You feel your own energy stretching thin. You feel yourself relaxing, cooling, shifting to red. You are aging, but you are not dying. You are simply changing your tune. You are harmonizing with the growing universe. By the time you hit the mirror of a telescope on Earth, you are a long, gentle wave. You carry the news of a universe that was smaller, hotter, and more violent. You are a memory made of energy. This redshift is the color of deep time. When you see a photo of deep space filled with tiny red specks, you are seeing the oldest things in existence. The redder they are, the older they are. It is a visual sorting of history. Blue is now, yellow is then, red is ancient, infrared is primordial. The universe is a time machine, and redshift is the dial. As we drift through this chapter, thinking of the stretching light, we can feel a sense of melancholy. The universe is flying apart. The connections are breaking, but there is also beauty in it. The expansion is what allows the universe to cool. It is what allows the sky to be dark so that life doesn't burn up. It is what gives us a future. If the universe were collapsing, the light would be blue-shifted. It would get more energetic. The radiation of the Big Bang would be compressed back into gamma rays. The sky would become a furnace. We need the redshift. We need the tired light. It is the condition for our existence. In the next chapter, we will confront the force that is driving this stretching. We will look at the engine of the expansion. We will stare into the face of dark energy. We will explore the vacuum energy of empty space. We will ask why the universe is pressing the accelerator pedal. We will see how this mysterious force, which makes up 70% of reality, will dictate the ultimate fate of everything. Will it tear the atoms apart? Or will it simply leave us in a cold, eternal isolation? For now, imagine the light waves passing through your room. Radio waves from distant quasars, stretched by billions of years of travel. They pass through your walls, through your body, silent and invisible. You are bathed in the stretched light of the cosmos. You are standing in the flow of the expanding river. Feel the space around you. It is not static. It is growing. Slowly, quietly, relentlessly. Rest in that expansion. Let your mind stretch with the light. We have walked through the invisible scaffolding of dark matter. We have seen how it acts as the glue of the cosmos, holding galaxies together against the centrifugal force of their own rotation. We have seen it as the great preserver, the gravity that builds structure out of chaos. But gravity has a rival, a dark twin, and this twin does not want to build, it wants to tear everything apart. To understand this new mystery, we must look at the motion of the universe itself. For thousands of years, humans believed the cosmos was static. The stars were fixed in crystal spheres, eternal and unchanging. Even Isaac Newton, with his laws of gravity, assumed the universe was a stable stage upon which the drama of planetary motion played out. But in the 1920s, an astronomer named Edwin Hubble climbed the peaks of Mount Wilson in California. He pointed the largest telescope in the world at the fuzzy patches of light known as nebulae. At the time, we thought these were clouds inside our own Milky Way, but Hubble realized they were not clouds. They were islands. They were entire galaxies, millions of light years away. And they were moving. When Hubble analyzed their light, he saw that it was stretched. It was redshifted. Just as the siren of an ambulance drops in pitch as it drives away from you, the light of these galaxies was dropping in frequency. They were rushing away from us. And the further away they were, the faster they were fleeing. This was the discovery of the expanding universe. Space itself was stretching, carrying the galaxies along with it like debris floating on a swelling river. It meant the universe had a beginning, a moment when everything was close together, the Big Bang. But for decades, astronomers assumed that this expansion must be slowing down. It was a matter of common sense. It was a matter of gravity. The universe is full of matter, stars, gas, dark matter, and matter pulls on matter. Gravity is an attractive force. It acts like a brake. Imagine throwing a ball into the air. It rises, but as it rises, the gravity of the Earth pulls it back. The ball slows down, stops, and eventually falls back. Scientists believed the universe was like that ball. The initial kick of the Big Bang sent the galaxies flying apart, but the gravity of all the mass in the cosmos should be pulling them back together. The only question was, is there enough mass to stop the expansion completely and cause a big crunch, where everything falls back into a fireball? Or is there just enough mass to slow it down forever so it coasts into a gentle stop? No one doubted that it was slowing down. Gravity always wins. Then came 1998. Two teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, set out to measure this deceleration. They wanted to see how much gravity had slowed the universe over the last few billion years. They wanted to weigh the universe. To do this, they looked for standard candles. These are objects whose true brightness we know perfectly. Specifically, they looked at type Ia supernovae. These are exploding white dwarf stars that always detonate with the exact same luminosity. They are cosmic light bulbs of a known wattage. A white dwarf star is the corpse of a sun-like star. It is dense and stable, but if it has a companion star nearby, it can steal gas from it. The white dwarf gets heavier. When it reaches a precise limit, the Chandrasekhar limit, about 1.4 times the mass of the Sun, it can no longer support its own weight. It collapses and explodes. Because they always explode at the exact same mass, they always release the exact same amount of light. This makes them perfect yardsticks. By measuring how bright these explosions appeared on Earth, the astronomers could calculate exactly how far away they were. And by measuring their redshift, they could calculate how fast they were moving. They pointed their telescopes at the darkest patches of the sky, looking for these dying stars in distant galaxies. They were looking back in time, billions of years, to see how fast the universe was expanding back then compared to now. They expected to see the curve bending downward. They expected to see the brakes being applied. They expected the distant universe to be expanding faster than the modern universe, showing that gravity was doing its job. But when they processed the data, the numbers didn't make sense. They checked their telescopes. They checked their math. They checked the dust in the galaxy to see if it was blocking the light. The result remained the same. The universe was not behaving as it should. The distant supernovae were dimmer than they should have been. They were farther away than they should have been. This meant that the universe hadn't slowed down in the past. It had sped up. The expansion wasn't decelerating. It was accelerating. The ball thrown into the air wasn't falling back down. It was shooting upward faster and faster, as if a rocket engine had suddenly ignited mid-flight. This discovery shook the foundations of physics. It meant that gravity, the force that holds the world together, was losing the war. Something else was out there. Something that acted like anti-gravity. Something that pushed space apart. We call this force dark energy. And just like dark matter, we have no idea what it is. It is a label for our ignorance, but we know it is powerful. In fact, it is the dominant force in the universe. When we do the accounting of the cosmos, the numbers are humbling. Normal matter, the atoms that make up the stars, the planets, the oceans, your body, every book ever written, every structure ever built, makes up less than 5% of the universe. 5%. Dark matter makes up about 27%, and dark energy makes up the rest, 68%. Everything we can see, touch, or understand is just the foam on top of a vast, dark ocean. We are the rounding error in the universe's budget. The universe is mostly made of a mysterious energy that wants to tear it apart. We are living in a minority state. But what is it? The leading theory takes us back to Albert Einstein. When Einstein first formulated general relativity, he found that his equations predicted a dynamic universe, one that was either expanding or contracting. But like everyone else at the time, he believed the universe was static, eternal. To fix his equations, to stop the universe from collapsing under its own gravity, he added a fudge factor. He introduced a term called lambda, the cosmological constant. It represented a repulsive force inherent in empty space itself. It was a mathematical prop to hold up the sky. When Hubble discovered the expansion, Einstein threw lambda away. He called it his greatest blunder. He thought he had missed the chance to predict the expanding universe. He thought it was an artificial addition that had no place in reality. But in 1998, the blunder returned. It turns out Einstein was right, but for the wrong reason. The cosmological constant appears to be real. It suggests that empty space is not empty. It has energy. This is a profound concept. We tend to think of space as nothingness, a void where things happen. But quantum mechanics tells us that the vacuum is alive. It is seething with virtual particles popping in and out of existence. It has a vacuum energy. This energy is a property of space itself. It is built into the fabric. And because it is a property of space, it does not dilute. Think about a box of gas. If you expand the box to double its size, the gas becomes half as dense. The atoms spread out. The gravity of the gas becomes weaker. Matter gets diluted by expansion. But dark energy is different. If you expand the box, you create more space. And because you have more space, you have more dark energy. The density stays the same, but the total amount of energy grows. It is the ultimate free lunch. This creates a runaway effect. As the universe expands, it creates more space. That new space contains more dark energy. That extra energy pushes the universe apart even faster, which creates even more space, which creates even more energy. It is a feedback loop of expansion. Gravity, which depends on matter, is getting weaker as the galaxies drift apart. But dark energy is staying strong. It is winning the tug of war. It has been winning for about 5 billion years. Before that, when the universe was smaller and denser, gravity was stronger. The universe was decelerating. But as the universe grew, the matter spread out and the balance tipped. We crossed the threshold. We are now living in the era of acceleration. So, what is the fate of a universe dominated by this push? It points toward a lonely future. It points toward isolation. Right now, we see billions of galaxies, but the space between us and them is stretching. Eventually, the distant galaxies will be pushed away faster than the speed of light. They will cross the cosmic event horizon. Their light will no longer be able to reach us. It will try to swim toward us, but the river of space will carry it backward. One by one, the galaxies will blink out. They will fade into the red and then vanish. The night sky will grow empty. In 100 billion years, any civilization living in the Milky Way, which will have merged with Andromeda by then, will look up and see nothing. They will see their own island of stars, bound by its own strong gravity. But beyond that, there will be only darkness. They will have no way of knowing that there was ever a Big Bang. They will have no evidence of the expanding universe. The traces of our history will have been erased by the expansion. They will think they are alone in an eternal, static void. We are living in a privileged time, the only time when the history of the cosmos is readable. But there is a darker possibility, a scenario called the Big Rip. This depends on the exact nature of dark energy. If dark energy is constant, like Einstein's lambda, then the galaxies will move apart, but structures held together by strong gravity, like our solar system or our bodies, will remain intact. We will be lonely, but safe. But if dark energy is something called phantom energy, if its density increases over time, then the future is violent. The repulsive force will grow stronger and stronger. First, it will overcome the gravity holding the galaxy together. The Milky Way will be torn apart. The stars will be scattered into the void, lonely wanderers drifting in the dark. The spiral arms will dissolve. Then, the force will grow strong enough to overcome the gravity of the solar system. The Earth will be ripped away from the sun. The planets will drift off into the cold, untethered from their star. Then it will overcome the electromagnetic force holding the Earth together. The planet will explode. The mountains will float away into space. Finally, in the last fraction of a second, the force will become infinite. It will overcome the strong nuclear force. Atoms themselves will be torn apart. The electrons will be ripped from the nuclei. The protons and neutrons will be shredded into quarks. The fabric of space-time itself will fray and snap. Everything in the universe will be torn asunder. This is the Big Rip. It is the ultimate victory of expansion over structure. It is the shredding of reality. Most physicists believe the Big Rip is unlikely. The Big Freeze, the lonely, cold, eternal expansion, is the more probable outcome. But the fact that we can calculate the shredding of atoms shows just how powerful this mystery force is. There is a profound irony here. Gravity, the force that gathers, the force that builds stars and planets and allows for life, is a local phenomenon. It works best at short ranges. It is the force of intimacy. It brings things together. Dark energy is the force of isolation. It is the force of the void. It creates distance. It turns neighbors into strangers. It is the antisocial tendency of the universe. The history of the universe is the history of the battle between these two titans. For the first 9 billion years, gravity held the upper hand. It slowed the expansion. It built the galaxies. It created the stage for life. But now, the tide has turned. Dark energy has taken the wheel. The universe is stepping on the gas. We are rushing toward a future where isolation is the norm. This realization has thrown physics into a crisis. It is the biggest problem in science. Our best theory of the very large, general relativity, works perfectly for gravity. Our best theory of the very small, quantum mechanics, works perfectly for atoms. But when we try to use quantum mechanics to calculate the value of the vacuum energy, dark energy, we get an answer that is wrong. Wildly wrong. When physicists sum up the energy of all the virtual particles in empty space, they get a number that is 10 to the power of 120 times larger than the dark energy we actually observe. That is a 1 followed by 120 zeros. It is the worst prediction in the history of science. It means we are missing something fundamental. We do not understand the vacuum. We do not understand the nature of nothingness. Is it possible that gravity acts differently on huge scales? Is it possible that our understanding of time is wrong? Is it possible that there are other dimensions leaking gravity away? These questions lead us to the final frontier of our story. We have looked at the heavy masses curving space. We have looked at the invisible energy pushing space apart. Now, we must try to unite them. We must look for the theory of everything, a theory that can explain the singularity of the black hole and the moment of the Big Bang, a theory that marries the smooth curves of Einstein with the pixelated jitter of the quantum world. In the next and final chapter, we will walk the edge of this frontier. We will look at the attempts to bridge the gap. We will look at string theory and loop quantum gravity. We will ask if gravity is even a fundamental force, or if it is an illusion, an entropic effect, like heat. We will look at the idea that space-time is not the stage, but the actor, made of tiny, discrete atoms of space. We will explore the texture of reality itself. We will ask what happens when the expansion reaches infinity. For now, let your mind expand. Feel the space in the room. It looks empty, but it is not. It is alive with energy. It is pushing against the walls. It is pushing the galaxies away. The universe is breathing out deeper and deeper into the infinite. And we are floating in the breath, held together by the gentle, stubborn pull of gravity, huddled against the dark. Imagine the Earth, the Sun, the Milky Way, all holding hands in the dark, resisting the tide. We are the resistance. We are the structure. We are the island of form in a sea of expansion. Rest in the center of that gravity. You are held. You are solid. You are here. We have traveled from the violent inflation of the first second to the silent, accelerating drift of the modern cosmos. We have seen how the universe grew from a singularity into a vast, structured web of galaxies. But there is one final question we must face. One final mystery that lies at the heart of the expansion. We know that space is stretching. We know that the distance between galaxies is growing. But what is space? When we say the fabric of the universe, is it a metaphor or is it a physical reality? If the universe is expanding, does that mean the fabric is getting thinner? Or is new fabric being woven out of nothing? To answer this, we must zoom in. We must leave the scale of galaxy clusters and descend to the smallest scale imaginable. We must look at the grain of the canvas itself. According to Albert Einstein and his theory of general relativity, space is smooth. It is a continuous sheet. You can zoom in forever, and it will always be smooth. It can curve, it can stretch, but it has no parts. It is a seamless whole. But quantum mechanics tells a different story. It tells us that nothing in the universe is smooth. Everything is made of particles. Everything is pixelated. Energy comes in packets. Matter comes in atoms. Light comes in photons. Why should space be any different? Physicists are now searching for the atoms of space. This is the frontier of loop quantum gravity. It suggests that space is not a background stage, but a physical mesh. It is made of tiny, interlocking loops of gravitational field. These loops are incredibly small, a trillion times smaller than an atom. In this view, the expansion of the universe is not a stretching of rubber. It is a chemical reaction. As the universe grows, the atoms of space are dividing. New loops are being born. The network is adding nodes. Imagine a crystal growing in a dark solution. New facets appear. The structure gets larger not because the atoms are swelling, but because more atoms are joining the lattice. The expansion of the universe might be the continuous crystallization of space itself, emerging from the vacuum. This changes how we view the dark energy that drives the expansion. If space is made of particles, then empty space is not empty. It is a boiling ocean of quantum activity. Virtual particles pop in and out of existence. Fields vibrate. Every cubic centimeter of vacuum contains energy. This is the zero-point energy. It exerts a pressure. It pushes outward. As the universe creates more space atoms, it creates more of this energy, which pushes harder, creating more space. It is a self-feeding engine of growth. Rate 100%, pitch 1%. But this engine has a destiny. It points toward a future that is vast, cold, and quiet. Let us travel there. Let us follow the arrow of expansion to its logical conclusion. We leave the present day behind. We jump forward not in years, but in eons. In about 100 billion years, the expansion will have done its work on the sky. The distant galaxies, the ones we currently see with the Hubble and James Webb telescopes, will have drifted so far away that their light can no longer reach us. They will recede faster than the speed of light. They will cross the cosmic horizon and vanish. One by one, the lights of the universe will wink out. The view from the Milky Way will change. Eventually, the only thing visible in our sky will be the stars of our own local group. The Milky Way and Andromeda will have merged into a single giant elliptical galaxy. Its gravity is strong enough to hold it together against the push of dark energy. But everything outside this island will be gone. An astronomer born in this distant future would look up and see a static, dark void surrounding their home. They would have no way of knowing that there was ever a Big Bang. They would have no way of knowing that other galaxies existed. the expansion will have erased the history of the cosmos. We are living in a privileged time. We are living in the only era where the universe is transparent enough to see the beginning, but close enough to see the neighbors. We are the keepers of the memory. But time marches on. We move from the stelliferous era, the age of stars, to the degenerate era. The supply of gas in the galaxy will run out. No new stars will form. The existing stars will burn through their fuel and die. The massive blue giants go first, then the yellow suns like ours. Finally, the red dwarfs, the tiny, frugal stars that can live for trillions of years, will flicker and fade. The universe will go dark. The only light will come from the faint glow of white dwarfs, the cooling embers of dead stars, and even they will cool. They will become black dwarfs, cold, dark balls of carbon drifting in the silent gravity of the galaxy. The expansion continues. The voids between the dead galaxies grow wider and wider. The isolation becomes absolute. Then even the matter begins to decay. If our theories of particle physics are correct, the proton is not stable. Over timescales of 10 to the power of 34 years, protons will break down. The dead stars will dissolve. The planets will evaporate. The solid matter of the universe will turn into radiation, into light and neutrinos. The structures we worked so hard to build, the rocks, the crystals, the bones, will simply melt away into the void. This leaves only one ruler, the black hole. We enter the black hole era. The universe is a sea of darkness, populated by the supermassive ghosts of the ancient galaxies. They drift in solitude. They have swallowed everything else. But as we learned in previous journeys, even black holes are not immortal. They leak. Through the quantum process of Hawking radiation, they slowly evaporate. They shine with a cold, faint light in the absolute dark. It takes a Google years, a 1 followed by 100 zeros, for the last black hole to disappear. But the universe has infinite time. It can wait. One by one, the black holes will shrink, get hotter, and finally explode in a burst of gamma rays. The last structures of the cosmos will vanish, and then we reach the end, the dark era. The universe is now a soup of photons and particles, spread so thin that they almost never interact. The temperature drops to absolute zero. The expansion continues, stretching the light until it has almost no energy left. Entropy has reached its maximum. The universe has reached heat death. This sounds terrifying. Death is a word that carries fear for us biological beings. But in the language of thermodynamics, heat death means equilibrium. It means peace. It is a state of perfect stillness. No more storms, no more collisions, no more suffering. The tension that began with the Big Bang, the separation of forces, the clumping of matter, the struggle of life, has finally been resolved. The universe has exhaled. It has expanded until it can expand no more. It has smoothed out every wrinkle. It has become a perfect, silent lake. But is this truly the end? Physics offers a loophole, a whisper of hope in the dark. The physicist Sir Roger Penrose has proposed a theory called conformal cyclic cosmology. He argues that in the far future, when all matter has decayed into light, the universe loses track of scale. For a photon, there's no time and no distance. A universe filled only with light has no clocks and no rulers. It forgets how big it is. And in that forgetting, a strange mathematical transformation happens. The infinite, cold, expanded universe becomes mathematically identical to the infinitesimal, hot singularity of a Big Bang. The end becomes the beginning. The heat, death of one eon, becomes the Big Bang of the next. It suggests that the expansion is not a line, but a circle, a breathing. The universe expands, dissolves into light, and in that dissolution is reborn to expand again. We do not know if this is true, but it resonates with the rhythms we see everywhere else in nature. Day and night, summer and winter, life and death. Why should the universe itself be any different? But let us return from the Google years. Let us snap back to the present, to the now. We are living in the golden age. We are living in the brief, beautiful window where the universe is active. Gravity is strong enough to hold us together. Dark energy is weak enough to let us see the neighbors. The stars are burning. The planets are warm. The mind is awake. The expansion is happening all around us, but here in our solar system, we are safe. We are an island of structure. Feel the solidity of the bed beneath you. That is gravity winning the war. Feel the air in your lungs. That is matter holding together against the void. You are the resistance. You are the universe's refusal to be empty. For billions of years, atoms have gathered, fought against the entropy, and built complex forms. They built stars. They built Earth. They built you. Every thought you have, every dream you dream, is a defiance of the drift. It is a spark of order in a universe that wants to spread out. As you lie here, suspended in the quiet expansion, remember that you are part of the fabric. The atoms in your body were forged in the fires of the past. The space you occupy is fresh, new space, carried along by the flow of time. You are drifting, but you are not lost. You are exactly where you need to be, in the center of your own observable universe. The expansion is not something to fear. It is simply the universe making room for time, making room for possibility, making room for rest. Let the vastness comfort you. Your problems are small against the scale of the galaxies. Your worries are fleeting against the scale of the eons. The universe is large enough to hold it all. It is large enough to absorb every sound, every light, every thought, and wrap them in silence. Let go of the day. Let go of the need to hold things together. The gravity of the earth has you. The flow of the cosmos carries you. Drift into the quiet. Drift into the expansion. May your sleep be as deep as the void, and your dreams as bright as the first stars. Good night.